Hello everyone, we want to talk about applications of dot product in this mini lecture. So in physics, there is a formula for something that is called work. Work in physics, mechanical work, is defined as the product of force and displacement. And force and displacement, we know that both of them are vector quantities. But work itself happens to be a scalar quantity in physics. For work or energy, we do not need any direction, okay? So the question is, what kind of multiplication is this that we are multiplying basically two vectors and we end up with a scalar? And guess what? Yes, it is a dot product. So if you have a force vector and you find the dot product of that force vector with the displacement, then the outcome is what we call it work in physics. And sure enough, that is the same as magnitude of F times magnitude of the displacement vector times the cosine of the angle in between the two vectors, force vector and displacement vector, of course. And we see that this is a number, it's a scalar. The dot product is a scalar, and work is also a scalar. Therefore, work is just a number with no direction. It only has unit of measurement. Force is measured in newtons in the SI system of units in physics, and displacement is measured in meters. So newton and then meters. Now, the unit of measurement for joules, for work is joules, okay? And for force, we say newtons. For displacement, it's meters. And for work, it is shown with capital J, and that is joules, unit of measurement for measuring work. If you exert a force of 1 Newton at the distance of 1 meter, then it is generating a work of equivalent to 1 joule. We have a box here, and somebody is pushing this box forward with an angle that the force makes with the horizontal. That angle is 20 degrees. We know that the box moves forward 12 meters, okay? And we know that the amount of mechanical work done is 2041 joules. We want to kind of work backwards and find out what was the initial amount of the force applied on this box at an angle of 20 degrees with the horizontal, such that the box moved 12 meters forward and it did work equivalent to 2041 joules. So we have to use the dot product formula, or the definition of work from physics, which is force times displacement. Okay, so we're going to say the work here is like 2041, and the amount of force exerted on the box we don't know, so I call it magnitude of F, and the displacement magnitude was 12 meters, and the angle is, of course, 20 degrees. So if you think about it, we have two vectors here. One is the force vector, okay, and one is the displacement vector, which is like that. Displacement is horizontal. Force makes an angle of 20 degrees with the horizontal, which means that the angle between the two vectors must be 20 degrees. So you see that I did draw the two vectors tail to tail. The angle they're making with respect to one another is 20 degrees. Vector D is horizontal, it's like 12 meters in terms of its magnitude. And vector F, we don't know its magnitude, we want to find out, and that's why we're using this dot product formula. So from here, we're going to say magnitude of F equals 2041 divided by 12 cosine of 20, and we are going to use a calculator to see what that is. So 2041 divided by 12 times cosine of 20, 181 newtons. Okay, 181 newtons. So that force is 181 newtons, and it is at a direction of like 20 degrees with respect to the horizontal. So I should say perhaps east 70 degrees south, or I can say south. Um, yeah, no, I can say east 20 degrees south, I guess, right? So what did I write? So east, this is east 20 degrees south. So that would be the direction for the force vector. Of course, they were just asking us to find the magnitude, which is 181 newtons, done. But if you want to mention the vector, including its direction, that's what you can say. East 20 degrees south. That's the direction of force vector. Or you can use true bearing coming from north. It would be like 90 plus 20, 110 degrees, okay? Or you can just write down 20 degrees below the horizontal, or any kind of direction appropriate you can use there. Another application is when you have two vectors and you want to find the angle in between. So here we have vector u in Cartesian form, 6, -5. So roughly I would say 6, -5 is something like this. And vector v, -1, -3 is something like that. So basically we want to find the angle between the two vectors. Okay, the diagram is not drawn to scale, of course. So I'm going to use the dot product formula. I'm going to say dot product is equal to magnitude of u times magnitude of v times cosine of theta, right? If you cross multiply this formula, which I solved for cos theta, that is actually the formula for the dot product. So I use the dot product formula and I solve for cos theta. And now in the numerator, I go 6, -5, dot -1, -3. In the bottom, that's 6 squared plus 25 and 1 plus 9. Okay, we know the formulas and everything. And if you do the math, you are going to get cos theta equals, I would say 9 over root 61 root 10, because 1 plus 9 is 10. 6 squared is 36, plus -5 squared, which is 25. So 25, 36, that's 61 right there. Now from here, theta would be inverse cosine of that figure. So 9 over root 61 root 10. And if you use a calculator, the answer will be 69 degrees, rounded to the nearest degree. So this way we can use the dot product to find the angle between two vectors. So that is the second application of dot products. First application in physics comes from the work formula. Second application is finding the angle between the two vectors. A third application right now I want to talk about, and let me separate these. Okay, so application 1, application 2. Okay, so I'm separating them. 1, 2, and now 3. The next one is called projection of a vector. When you have two vectors, vector v and vector u, the projection of vector v onto vector u is defined as this vector here on vector u, where the tail is the same as the tail of vector v, but the tip is actually the foot of the perpendicular that you drop from the tip of vector v onto vector u. So this blue vector here you see is called projection of vector v onto vector u. And it is a vector itself. That's why we have the arrow on top of PROJ. And vector v is a vector u is a vector, so I put like 3 arrows here, basically, because projection vector is a vector itself. Now, this vector has a magnitude that is equal to actually the adjacent side in this right angle triangle. Hypotenuse times the cosine of theta would be the adjacent side. So magnitude of v, which is hypotenuse, times cos theta, That is actually the size or the magnitude of this so-called projection vector. But then if you multiply this expression by magnitude of u in the top and bottom, okay, in the numerator you generate basically dot product. So basically projection vector uh, magnitude of projection of v onto u is actually the dot product of the two vectors divided by the magnitude of vector u. So this is some sort of formula we derive. Now this is the size or the magnitude of this. Now if I had the unit vector along vector u, and I would multiply the size or magnitude of this vector by that unit vector, I would end up with actually a vector, okay? And that vector would be the projection vector of v onto u. So I need to have this so-called unit vector u hat on this vector u, and if I multiply this unit vector by the magnitude of the projection vector, then I would have the actual vector itself. So in order to do this, I'm multiplying what I just derived by u hat. But u hat itself is vector u divided by magnitude of vector u. We have discussed this in the past. So if you multiply the bottom by magnitude of u, and in the numerator you have vector u itself, then you end up with this new formula. And then magnitude of vector u all squared is nothing but the dot product of itself. It was one of the properties of the dot product I explained in the past. So basically it becomes u dot v over u dot u. And this is just a fraction. It's a scalar. It's a number. And when you multiply this by the vector u itself, okay, then you end up with a vector. And that vector is called the projection vector of v onto u. And that is the proof of the formula, basically. I want to apply this in this example. We have two vectors. We want to find the projection vector of A onto B, as simple as that. Okay, so what I'm going to do, I'm going to write the formula. I'm going to say projection of vector A onto vector B is equal to A dot B, I should say here, A dot B divided by, we want to find projection of A onto B. Here it was V onto U. So the bottom is U dot U. Here it's going to be actually B dot B, right? B dot B. And this would be a scalar times vector U itself. In this case, it will be vector B, okay? So that's vector B. So that's the formula tailored for our question. Now the rest is not that hard. 2 comma negative 3 dot 1 comma 4. That will be the dot product in the numerator. In the denominator we have b dot b, so that's 1 comma 4 dot itself, and then we have vector b 1 comma 4. Okay, so we end up with the dot product will be 2 times 1 plus negative 3 times 4 over 1 times 1 plus 4 times 4, and then times 1 comma 4. So the top is negative 12 plus 2 is negative 10. The bottom is 16 plus 1, which is 17. So that is the scalar I was talking about earlier. That's negative 10 over 17. And we're going to multiply this scalar by the vector 1 comma 4. So negative 10 over 17, negative 40 over 17. This is actually the vector we were trying to find. The projection of vector A onto vector B is a vector itself, and that is the answer for this vector. Okay, so how did we get this answer? By using dot product. So this was another, or actually the third application of dot product, other than the work and the angle examples. This is another one, and you can always use this formula. And I'm sure you're taking notes, and I'm sure you're watching these lectures in and out several times, not once, because by watching it once, you may not get everything, obviously. You rewind and you fast forward and you double check everything, you take notes, you write the formulas down, you read the examples in the textbook, and you do this constantly every single day without even wasting one day. and after like 1 or 2 weeks, you get hang of the material. Okay, so good luck practicing.